Okay, welcome guys. Before we get started, I want to go over a couple things. First thing, I put a bunch of stuff up on Blackboard. I sent out announcements, so you probably got a text, or if you got your phone synced to Blackboard, your phone should have went off. But make sure you look. There's two quizzes up there. Well, the one I told you about, that's the reactant sheet that we did last time. I told you I was going to decide if I was going to make it a quiz or make it a homework, and I decided to go ahead and count it as a quiz. And then I put, I think that's two quizzes I put up there. You just got to look at it. So I got a lot of documents on the stuff that we started on last time, which was we started on AC series circuits. So that all that stuff is up there through AC series parallel. So at some point you want to download that and put it in your notebook. So you'll need a couple of those documents today. So make sure you look in Module 3, the Module 3 folder. Um, the other thing I want to say is that I mentioned, I don't know, I didn't make a big deal out of it. I told you I was thinking about doing away with the exams and just having quizzes. Because of the short semester, I didn't really know how to break it up into the four quizzes, the four exams and quizzes that I normally have. So what I did for all the other classes, I just give them quizzes. But since you guys were majors, I felt like the course, I felt like the quiz might be a little bit too easy. You know, it needs to be challenging. But considering the circumstances, I think I'm going to go ahead and do that. Eliminate the exams. And what they will do, the bad news is it makes the quizzes count a lot more. The good news is there's more quizzes than there would have been exams. So they count more, but you have more of an opportunity to improve your grade. So it really works in your favor. And had we been a normal 15-week session, face-to-face, or even 15-week remote like we're doing now, I would never ever do that because I just think it makes it too easy. But I think I'm going to be forced to do that. So I'm going to redo the syllabus. Now, what that means is that you guys really need to take the quizzes seriously. So what I'm saying is don't miss a quiz. It's still, the Blackboard is still top the two lowest. You'll have more than 10 quizzes in the end. I think we're just up to like quiz 3 or 2 or 3 right now, but I'll be giving you extra credit as we go along, extra assignments you can do on the side that counts as quiz grades. So, I mean, it's kind of a break for you, a good break, because you'll probably end up doing, unless you try really hard to mess it up, you'll probably end up doing pretty well in the course since we're doing it this way. So I'll have to update the syllabus. At the bottom of the syllabus, I have always my line is I reserve the right to change the contents of the syllabus at any time, and so this is one of those times I'm gonna use that. So I'm going to eliminate the exams, and we'll just have quizzes. I don't know how many, probably a lot of them, because I broke the course up into modules. And so just 15 weeks, we'll have modules. And a module to me is a group of logical material that kind of goes together. So other than that, I think you guys have any questions or comments before we start? Okay, well, what I want to do, I put a problem on the board, and this is actually, if you've been to Blackboard already, this is one of the problems, one of the topic sheets, one of the practice sheets off of Blackboard. So if you go to the Module 3, you'll actually have the handout. The good thing about having the handout, the one that, if you look at Module 3 on Blackboard, the first thing I give you is a topic sheet, which shows you the steps that you go through when you solve a series AC problem. So I highly recommend you print that out, and I highly recommend you put in your 3-ring binder. So if you look at that, though, you'll see what I'm saying. If you look at that topic sheet, it shows you the step by step in the correct order how to go through and solve a series AC problem. And then the next sheet is a practice sheet. It's actually the one we did last time we were together. But you'll see that the sheet is broken down exactly as the topic sheet says. So if you read the topic sheet and then you look at that example problem we did in class last time, you'll see we follow each step exactly. Well, we're going to do the same thing with this one. Only well, you guys have all the information. I want you to try to work it first, and then we'll work it together. Now, on this problem, we're going to introduce a new topic. You guys know power. We talked about power in DC. And you know power is basically V times I. definition of power. Power is energy per unit time, energy converted per unit time, or work done per unit time. We learned all about power in DC. Well, AC power is way more complex than that, or I should say way more involved than that. So what we're going to do today, we're going to talk about AC power, but not, you're just going to talk about a portion of it, a small bit of AC power, because AC power requires a whole lecture time. We'll spend a lot of time on AC power. So, but we will be able to do kind of slightly to AC power as you go through this example problem. So what I'm going to do, hopefully you have the sheet printed out. If you don't have it printed out, yeah, I think you can minimize your collaborate. If you go to Blackboard, you'll see the sheet and you'll see the problems. I will say I'll read it, but you need to have the sheet in front of you. So it either needs to be printed out or you need to bring it up on your screen so you can see the steps. And just take out a sheet of scrap paper and solve the problem. So I'll read it real quick. I'll read the first 6 steps. It says the first thing is to convert the power source to phasor form. Convert power source to phasor form. Number 2, they want you to find the total impedance. Number 3, they want you to draw the impedance diagram or the impedance triangle, which we talked about that. They want you to find the voltage across the resistor and the voltage across the inductor in both polar and rectangular form. They want you to prove KVL. And they want you to, it says using a straight edge and protractor, draw the phasor diagram for the circuit. We'll try to do that. I don't have a protractor, but so if you don't have this, bring it up on your computer. I'm going to step out of the frame of the camera, give you maybe 10 minutes or so to work on this, and then we'll come back. We'll go through it together. I don't care if you have the other sheet out, the one we did last time. I just want to make sure that the stuff is logical and that you kind of see exactly what we're doing. So I'll be quiet. It's according to my clock. It's 2:10 now. I'll come back at 2:20, and we'll see how far you got, and we'll work it and answer any questions. So I'll be right here. So we got about 2 more minutes, and then I want to go over the circuit. Okay, 2 minutes. Okay, 1 more minute left, and then we'll go over it. Okay, so let's take a look at this now. The first thing we have to do, it says convert the power source to phasor form. So there's two kinds of power sources. We've only dealt with one. There's voltage sources and there's current sources. This, of course, is the voltage. I want to convert it to a phasor. Convert it to a phasor, what I have to have is I got to have an RMS value and a phase angle. So this value is in RMS. So then if I get the RMS value for the phasor, what'd you get? Do I have to call on you individually? Well, let me look at you at the camera. I'm looking at my computer. I'm looking at, who do I see there? Dominic, Jacob, Tyler, Brandy, and the other people are hidden in the circle because I guess they called in. There's only one call in. Now somebody just signed on. Okay. Anybody how do you convert it to a phasor? What do? I need the RMS value from here, and the phase angle, of course, is 0. So somebody give me the RMS value.
RMS value is 100 volt.
So it's 100 volts and the phase angle, since the phase angle is 0 degrees and my units are volts, so I'll put it in a bracket like that. Now this is a phasor, so it's important that you show it like that. So I'm going to erase this script V. That script V represents an instantaneous voltage. I'm going to show it like this, which means you can now treat it as if it were DC. So I'm going to erase the script V and put the phasor notation. So this is now 100 angle 0 degrees. The units are volts. And now this is a V hat, which represents a phasor. So I'm going to get rid of this and this. So that was the first part of the problem. The next thing I wanted to do is to find the total If this were DC, we find the total resistance. In AC, we find the total impedance. So to find the total impedance, since I have a series circuit, I'm going to add the total oppositions. So Z is going to be the opposition from the resistor plus the opposition from the reactance. For the resistor, I got 3, and since this is a capacitor, since this is an inductor, you got to remember where it is in the impedance diagram. It has a positive J operator. Had this been a capacitor, we'd have a negative J operator, but notice I didn't show that. You have to supply it. So this is going to be plus J4. So that's my impedance. Right away, when you get that impedance, what you want to do is convert it from rectangular to polar form. You always want to have all oppositions available in both polar and rectangular form. So we convert it over. What you'll have, you want to find the radius vector, or I just call it the magnitude of Z. So I'll show it like that, the magnitude of Z, or you can use an R. But it's equal to, I'll write the formula, but I'm not going to do this all the time. So there's one for that, and then to get the phase angle, it's the inverse tangent of X over R. So those are the formulas we're going to use all the time, so you might as well go ahead and memorize those. So if we go ahead and do this, we got 3 squared plus 4 squared, square rooted. That's 9 and 16 would be the square root of 25, which is 5. So for our radius vector, we got 5 at an angle of, I got to do my inverse tangent of 4 over 3. So somebody give me the value of the angle. Now make sure you're in degrees. You always want to be in degrees unless you're doing something with a sine. Then you would be in radians. But for this one, what you get for a phase angle?
$53.13.
All right, so that sounds about right. All right, so we got 53.13 degrees. Now, that's an opposition, so it's in ohms. Now, what I'm going to do is just stick this over to the side over here. I'm going to say ZT. I'm going to show it in rectangular form as 3 plus J4. Just so I have it in case I need it. Then I'll show this form of it. ZT is 5 angle 53.13 degrees. All right, so now we got that. All right, so next thing it tells you to do, they want you to draw the impedance diagram based on, and when you draw the impedance diagram, you want to use it in rectangular form. It's easier. You could do it in polar, but rectangular is the easiest. So let me show you while they're looking for the impedance diagram. You can scale it if you want to. I never scale it. I just kind of estimate when I'm drawing these, unless I got to, if I was writing a textbook or something, I might put a scale on it, but you can just estimate it. So the impedance diagram looks like this. That's R, and that's X. And what we do is we go over on the R axis, the real axis, we go over 3 units. So I just kind of guesstimate 3 units over. And then we go up 4 units. If that was a minus J, we would go up 4 units, but we're going to go up 4 units. I make it a little longer than that. And that's J4 ohms. And then to find the actual impedance, what you do is just make a box or rectangle, And then the diagonal from the origin out to the corner becomes your impedance. So it will be like this. This represents your impedance Z. The angle right here, the impedance angle theta Z, that's this angle right here. That's 53.13 degrees. So this is the impedance diagram, and this represents your impedance triangle. You could just pull that off if you wanted to, and just because that's a right triangle, you can show the impedance triangle. Some people work off the impedance diagram. Some people work off the impedance triangle, which comes from the impedance diagram. I do both. I mean, it doesn't matter. So there's the diagram that you're looking for. Now it's good to know this because if I give you a quiz on this, it'll be just pretty much what we're doing. You just, for all practical purposes, copy it. Now, number 4, it says they want you to find the voltage drop across the resistor and the voltage drop across the inductor in both rectangular and polar form. The reason for that is you'll need it when we do the next step. So find VR and VL. So how do you find VR and VL? Well, just Ohm's law. If I had just all resistors in DC, I want to find the voltage drops. It's just V times I. I times R. And it's the same here. So I found I, so the first thing I got to do is find my current phasor. I'm taking my voltage phasor divided by my impedance, which is not a phasor, so I don't put a hat on that one. Put my numbers in there. I got 100 angle 0. I'm going to leave the units off, but you guys, if you're taking notes, you go ahead and write them on there so you have them. I got 5 angle 53.13. That's going to be 20. When I subtract this from 0, that gives me a negative angle, negative 53 point, and this would be amps. Right? Now, if you think about the impedance diagram that we just talked about, if you end up in this quadrant, you know you got resistance and a net inductive reactance. If you end up in this quadrant, you know you have resistance and a net capacitive reactance. When we're up here, we can tell this by our impedance angle phase, if you remember, was 53.1 degrees. So we know our impedance is here, right? Well, if you remember, when we talked about AC oppositions, I told you to remember the term Eli the Iceman. So Eli Ice Man. Now, since we're in quadrant 1, that means the reactance is a net inductive reactance. So that L stands for inductor, and I stands for, C stands for capacitor. So we're over here. And the way you read this is, if I have an inductor in the circuit, and the inductor is, if that circuit is, if the net reactance is inductive, and the voltage is going to happen before the current. If it's capacitance, then the current is going to happen before the voltage. We say the voltage leads the current, or the current lacks the voltage. I'm just saying that because at some point, I think the next step, they're going to have us draw something called a phasor diagram. This will be our first phasor diagram, but you'll see that this is true at that point. Let's go ahead and I'll come back to that. All right, so we got the current. I'm just going to put the current over here. And notice I'm drawing this just like we did in DC with the arrows, and we can treat it just like a DC circuit, even though it's really AC. So we got 20 angle minus 53.1, and my units are amps. So I got my current phasor right here. So I can get rid of this. And now I can answer the question they want. They want to know the voltage across the resistor and the voltage across the inductor. So VR, which is a phasor, is equal to I phasor times R, and VL, which is a phasor, is I phasor times XL. I phasor is 20 angle minus 53.13. I'm leaving off the units on purpose. And then now this, I got to supply the angle is 4, but in the Peters diagram, you know, resistance is at an angle of 0 degrees. So this is 4 angle 0. Again, I'm leaving off the units, but you should write it. If I write 20 times 4, do my math, this would be 80. So for this one, we get 80 angle minus 53.1, and that would be volts. So that gives me VR, VL, do the same thing. We're going to do 20 angle minus 53.13 times, oh wait a minute, I made a mistake. This R, this 4, that 4 was for the inductor. You guys should have caught me on that. So I got to flip these around. That 4 is for the inductor. So this actually is XL. This is R. All right. I just looked at that wrong. All right. So this is the voltage across my inductor, 80 volts. And now I'm getting the voltage across my resistor. So I got to supply. Oh, then if I do that, this is all wrong, isn't it? What does this need to be? What does that need to be? This is R, that's XL, that's XC. So in our Peters diagram, this really is 4, but it's 4 angle 90. So if I switch this over, I can't have that 0 there. Inductance by itself, just a pure inductor, has a angle or phase of 90 degrees. So I got to do a subtraction here. So how much is that? 90, 50, 40, 37, about 37 degrees. Something like that. You guys can do the actual number here. Okay, and then my I times R, so R is 3 angle 0. And so I got 60 angle minus 53.13. And this would be volts. All right. So there's VL and there's VR. You can get the decimal value here. I guess it's really 36 point something, 36 point. I can't do my head math right now, but about 36 point, around about 37 degrees. This one right here, 60. Now I want you to pay attention to something. Look at the phase on the voltage, resistor voltage. Look at the phase. Look at the phase on my current. Take a look at that. This phase is minus 53 degrees. The phase angle on my current is minus 53 degrees. Not true for my inductor. The phase is like 37 degrees. Remember when we talked about AC opposition, we mentioned that the voltage across a resistor is always in phase with the current through the resistor. So this will always happen. In every case where you have a resistor, the phase of the voltage drop and the phase of the current through that resistor should be exactly the same. So this worked out that way as we would expect. So we got this. Now what you guys got to do, they want us to show it in the voltage drops in phasor form, which I have here, but you got to convert them over to rectangular form. So I know you guys are not doing a lot of talking today, but you're going to have to convert these because I don't have a calculator. If not, we're going to have a lot of dead space on the video. And so I need for somebody to convert, maybe one person convert this to a rectangular form and convert this to rectangular form. And let me know what they are in rectangular form. So I'll write the phasor here, VL. So I need this value in rectangular form, and then another person can work on the other one, VR. So let me know when you got a value for either one of those.
I think I have the rectangular form for the resistor voltage.
Okay.
47.9 minus J 47.9.
Like this?
Yeah.
I don't think that's right. The only way you can get these to be the same, your angle would have to be 45 degrees. So let me put the equations on the board. You guys can calculate it. So to find the I don't know what to call it.
I think for VR we have 36 plus 36 minus 47.9 J.
36 minus 47.9.
Yes.
Okay. Anybody else get that one? Dominic, you want to try it again and see if you got that? You should have one would be 60 cosine.
Yeah, 60 cosine 36.87.
Yep.
Oh wait, let me make sure my calculator's in the right mode.
Yeah. Okay. Somebody give me a value for VL. Convert that over. This one.
63.8 plus 48.1.
All right. Now, the reason they had you do this, when you have a voltage or current phasor, you'll leave it in polar form. But on the handout, the next thing he says is show that KVL is true. Show that the voltage across the resistor plus the voltage across the inductor add up to total voltage. Well, if you do this, if you add 80 plus 60, that does not add up to 100. You can't do it that way though, because these angles here, you'd have to add. You need a protractor. You have to do that. It would be difficult to do. Not impossible, but it wouldn't be nice. It's much easier to convert both of these to rectangular form. Remember, when you add and subtract complex numbers, you want to be in rectangular form. So these two in rectangular form should equal this in rectangular form. Well, this in rectangular form, V hat equals 100 plus J0. So hopefully when I add these up, I get something real close to this value over here. Well, let's see. That's about 64, if I round it, 63.8, and that's about 36. So 64 and 36 is 100, or close to 100. And this, if I round it, 47 point, that's about 48 negative, and that's 48 positive. So if I add those up, I get something really close to 0. So that's how you prove Kirchhoff's voltage law. If on the quiz I say prove KVL, that's what you want to do. And then the only other thing, now this is new, number 6. It says using a straight edge and a protractor, draw the phasor diagram for the circuit. I don't think ever before we drew a phasor diagram, so let me show you how that's done and what a phasor diagram is. I'm going to erase this. Let me see here. I'll put it right here. So all the phasor diagram, remember a phasor is a rotating arrow. By convention, it rotates counterclockwise. So all of these are phasors. Anything with a hat on it is a phasor. So what I'm doing is I'm going to put all those phasors on a coordinate system. And remember, they're rotating, but let me draw a phasor and then we'll talk about it. So if I ask for a phasor diagram, you start out with a set of axes, and then all you want to do is put all your phasors down. Right off the bat, put this one down. Put that one down. So I'm going to show my total voltage right here as an arrow. That's VT. If you want to put 100 angle 0, you can. So that's my total voltage. That's one phasor. The total voltage, the total current, you always want to show those. So my total current is 20, but look where its phase is, minus 53. So I'm going to put it, that's in quadrant 4, because minus 53 is in quadrant 4. And I'm just going to kind of guess where it is, probably like right here. So that's I hat. Now, I'm going to stop for a second before I show the other two phasors. Remember, these phasors are rotating counterclockwise. They rotate, but what stays the same as they rotate is this angle right here. This angle stays the same. That angle right there is at negative 50, what's my current? Yeah, the negative 53 degrees. So even though they're rotating, the relative angle between the two phasors stays the same. So if my voltage phasor is like this, my current phasors 53 degrees away from it, and it's rotating counterclockwise, and this angle between them stays the same. When that Eli the Iceman came in, Eli Iceman, and since I don't have any inductance, all reactance since I don't have any capacitance, all my reactance is inductive. So in the inductive circuit, I'm going to see the current phasor before I'm going to see the voltage phasor before the current phasor. So imagine this is your eyeball right here. You're looking at these phasors rotate. Here's my voltage phasor, the long one, and this blue one is my current phasor. If they were rotating counterclockwise, you see the voltage first, you see the voltage first, and 53 degrees later, you see the current. So this little thing is good to remember which is leading and which is lagging. That turns out to be later on in the course. So this is my phasor diagram. Now I got to show the rest of my phasors. I got this one, VL, and I can use different colors on this to make it stand out. This is 80 at 37, so it's something like, it's not quite as long as that one. So it's probably like that. So that's VL. And then this one right here, the voltage across my resistor. Remember the current through the resistor and the voltage across the resistor are always in phase. And since it's a series circuit, that means that they're going to be right on top of each other. So when I draw that one, I'm going to draw that one like this. There's I, and I got to get right on top of that and phase with it. This is my VR. So there is a phasor diagram for this circuit. So the phasor diagram is something new. Okay? All right, now, power. Now we get to some new stuff here that'll start to shed some light on how power acts in the AC circuit. But again, power is really, really involved. So this is by no means the lecture on power. The lecture on power will be probably at least a whole session, maybe a session and a half. But I'll read number 7. It says, in AC, the power delivered to the circuit can be determined by PT equals EI cosine theta or VI cosine theta, where E and I are effective values or RMS values, and theta T is the phase angle between the voltage and the current. They want you to determine the power for the circuit. So let me put the formula on the board that he has there. So it says in an AC circuit, power delivered or power dissipated equals VT or ET times I T times cosine theta T. When you calculate power, you always calculate power using RMS values. So these are phasors. These are the magnitude of the phasors, not the angle. So I take the magnitude of my voltage phasor, this one, times the magnitude of my current phasor, this one, and I multiply that by the cosine between them. Now I showed you on the phasor diagram, which I erased, when the voltage is right here, and the current was down there, and that angle was minus 53.13 degrees. Okay, so we're going to take the cosine of that. Now, do you guys remember even and odd functions? Do you guys remember that from your math class? Even and odd function. Let me see if I can remember how to write it. So an even function if you take f of x and f of minus x, you get the same thing. They're equal to each other. F of x and f of minus x are equal to each other. And an odd function, if you take a negative x value, it makes the whole function negative. So let me see if I can explain this better. Cosine is what we call an even function. So no matter what I put in for x, I'll get a positive number back. The sine is an odd function, so if I put in one value, a positive value for x, I'll get a positive value back. If I put a negative value for x, I'll get a negative value back. That's what an odd function does. So let me see if I can show you on the graph. So a cosine looks like this. You know, cosine wave looks like this. And the sine wave looks like this. So an even function, no matter what value of x you put in, whether you put in a positive value of x or a negative value of x, the result you get is always positive. So like, let's say I chose this x right here. If I come up, my value for y, or this is f of x or y, my value for y is that value right there. If I chose this value but negative, then it's over here. And my value for y is still positive. So whether I put in a positive or a negative, I got a positive result back. Whereas on the sine, if I continue this waveform, there's a sine wave. If I chose this value for x, I come up, I see that value gives me a positive value. If I go over to the negative value for that same value but negative, it gives me a negative value down here. So the cosine is an even function. Now, if you want to know why is he talking about this math stuff, well, the angle you put in here is the angle between the voltage and the current. And strictly speaking, here's what it is. You remember from the phasor diagram. That I just showed you, the voltage was here, 100 angle 0. The current is there. It's like back here. So it's 20 angle minus 53.13 degrees. So what this says is that angle is the angle between the voltage and the current. Well, that angle turns out to be minus 53.13 degrees. So that's what you should put in here. But you can get it wrong and put in a positive and still get the right answer because the cosine is an even function. So I just want to be clear. It doesn't really matter, but I want you to know what you're doing. That's the only reason I'm telling you this. Strictly speaking, you should put this angle in there, minus 53.13 degrees is what should go in here. The angle between the voltage and the current is a negative 53 degrees. But if you slip up and put a positive 53, you still get the right answer because the cosine is an even function. The negative argument and positive argument come back the same. So having said that, let's go ahead and do the problem. So the problem is, it says in AC, the power delivered to a circuit can be determined by this. PT is V times I cosine theta, where E and I are RMS values, and theta T is the phase angle between E and I, or V and I. They want you to determine the power for the circuit. So let's figure it out. If I take V or E, that was 100 volts. So I got 100 volts. My current was 20 amps. Now notice I'm not doing anything with those angles. Those angles I don't have to use for power. The cosine and the angle between them will be cosine of minus 53.13 degrees. So somebody calculate this for me. 100 times 20 times cosine of minus 53 degrees, and let me know what that is.
At a 1200.84 watts, I guess.
Okay, so that's the power delivered to the circuit. Okay? Now, I'm going to read the next question. Number 8, it says, show that the power, and in parentheses they say, or energy. It says, show that the power or energy is conserved by using this equation. So they gave me this equation. I'll put it on the board for you. They have the total power is equal to the power from the resistor plus the power from the inductor. So to show that the power, and parentheses they say, or energy is conserved by using PT equals PR plus PL, where and then they give you this other equation based on this one. Okay, so I won't read it, but I'm gonna just do this. So back in DC, when you learned about power, you know, if I add up all the power dissipated, it has to add up, it has to equal the power, the total power from this voltage source, right? So that's what this is. He wants you to show that the total power given up by the source is equal to the power delivered over here to the resistor and to the inductor. So basically, prove that the left side of this equation and the right side of this equation are equal. In doing that, we're going to learn something about AC power. So the left side we already calculated, that's this. P delivered and P total are the same. So we did that. All we got to do is calculate the right side using this equation. So if I do that, what we got to do is write this equation for PR, and we got to rewrite this equation for PL. Right now it's written for PT. If I want to write it for PR, then what I do is I change these all to R's. I don't really have to subscript the T because this is a series circuit, so I'm not going to subscript the T. So change that for R's, and now this right here will give me that. The power dissipated by a resistor is equal to the voltage across the resistor times the current through the resistor times the cosine of the angle between these two. Is what that says. So that'll give me PR. So let's go ahead and do that. Let's go ahead and do this calculation. So VR was, I think this was VR right here. This was VR. So VR was 60. So right here, this is VR. This was 60 volts. The current was 20 amps times the cosine of the angle between them. Okay, well, what was the angle between them? What was the angle between VR and I? Well, if you remember in my phasor diagram, let me go back to that. VR was like down here. Well, here's I. I was at minus 53 degrees. Here's I. That's my current phasor. And if you remember, VR, which is right here, has the same phase angle. That's what I told you, that the current through a resistor and the voltage across it are always in phase. So that means that VR is sitting right on top of that current phasor, and they're both rotating together. So in other words, the angle between them is 0. So this is going to be the cosine of 0 degrees. If you know anything about the cosine of 0 is what? Anybody know? What is the cosine of 0 degrees? That's something you should remember. The cosine of 0 is 1, and the cosine of 1 is 0. And the cosine of the sine is the opposite. We'll do that in a second. So the cosine of 0, if you check it on your calculator, you'll see that that's 1. And then this goes away right here. That's a 1. So if I multiply these, I get basically 1200. 1200 watts. Now, let's do this one, PL. How do you write it for PL? Well, if I change this to a L, I change this to a L, PL, I gotta change all these to L's. VL, and then that's a L. So this says that the power dissipated by the inductor is equal to the voltage across the inductor times the current through the inductor times the cosine of the angle between these two. So now let's do that calculation, see what happens. So if I do that calculation, if you remember VL, what we got was 80 volts. The current was 20, still 20 amps. Cosine, what is the angle between the voltage and the current? That's two ways of doing that. You can look at your impedance diagram, or you can just use logic. It doesn't matter to me. You can either way.
It's real close to 90.
It's 90. Yeah, so it's 90. So that is the magic word right there. It's 90. If you don't see how you got that, you can look at the impedance diagram and just subtract the two. I think the VL was up here somewhere. Just find the angle between them. It's going to equal 90 degrees. And the cosine of 90 is what? What's the cosine of 90 degrees?
0.
It's 0. Cosine of 90 is 0. Well, 0 times all of this is 0. That means in this equation, let me go back to the original equation. That means that in the equation, PT, or P delivered, P delivered equals P from the resistor plus P from the inductor. But because of this whole thing right here is 0. This is 0. Which means P delivered equals P dissipated by the resistor. You can see what we got when we did that. Well, I think I erased it, but somebody told me the total power from the first calculation was 1200.8, and we got 12. Now it's off a little bit. I don't know why, but we got 1200. So that means this power is 0, and the total power and the power dissipated by the resistor are equal to each other. Now, you got to think about that for a minute. I think it even says on here, number 9. It says, what does your calculated value imply for PL? If this is 0, what does it imply if this is 0? You see why it's 0, because the angle between these two are 90, so it has to be 0. But what this says is the inductor does not dissipate power. The inductor does not dissipate power. Matter of fact, what you're going to learn is not only does the inductor not dissipate power, any reactive component, there's only two. There's the inductor and there's the capacitor. Neither one of them will dissipate power. Now, what I mean by dissipate, that's a DC thing. Current comes into a resistor, goes through a resistor, it heats up, and it dissipates that energy. That's power dissipation. So in a resistor dissipates power. In other words, it takes electrical energy and converts it to heat. If I have an inductor or capacitor, it doesn't dissipate power. Here's what it does. It stores the power, and then the power is sent back to the generator. So it kind of borrows the power and gives it back. So the net power dissipation is 0. Now remember, we're talking about an ideal inductor, ideal capacitor when we get to it. That means that I don't have any resistance in the inductor or capacitor, which you know can't be true. There's always resistance in everything. So this will actually dissipate a little power because of resistive elements. But we're speaking ideally here. In an ideal, perfect world, this inductor cannot dissipate power. It just holds the power for a minute and gives it back to the circuit. So that's another takeaway. I know this is a lesson that we already went through, series circuits, but now what we added to this was a phasor diagram. You learn how to do that. we did a KVL. We talked about KVL last time. We actually did the calculation for it. So the phasor diagram is new. The KVL, I showed you that, and now we're showing you AC power. And you're saying that reactive components, it's impossible for them to dissipate power. The power runs in and is stored in the magnetic field for a little bit. When the magnetic field collapses around the inductor, the power is sent right back to the generator. So the takeaway is reactive components, you might want the word ideal. Ideal reactive components cannot dissipate power. They can't convert energy to heat. And there's something else new. The last question here talks about something called power factor. Let me read it and then I'll write it on the board. It says power factor is determined, for power factor they abbreviate PF. The power factor is determined by PF equals cosine of theta, where theta is the angle between the total current and total voltage. The terms leading and lagging are often written in conjunction with power factor. They are defined by the current through the load. If the current leads the voltage across the load, then the power factor is leading. If the current lags the voltage across the load, then the power factor is lagging. They wanted us to determine the power factor for the circuit above. So let me write all that. I mean, it's a lot to read. But there's this new, it's not new, but there's a new term, power factor. Let me write it down. It turns out to be pretty important. So power factor. Comes from this. Okay, remember we said that the total power, the power delivered equals V total times I total times cosine of theta total. We talked about that. Well, you know, numbers that you multiply in math are called factors. So I'm multiplying this times this times this. So this is a voltage factor. This is a current factor. And what they're calling this is power factor. Power factor. They abbreviate it like that. Now, if you think about it, let's talk about a power factor of 1. That's the highest the power factor can be. And a power factor of 0. That's the lowest the power factor can be. The power factor is always given in numbers between 0 and 1. Well, let's think about this power factor right here. What will give me a 1? The only way I can get a 1 here is that the angle between these two right here would have to be 0 degrees. And the only time that happens is when you have a resistor. Remember, if I have a resistor, if this is my voltage, then my current is in phase with it. So the phase angle between the voltage and the current are 0 degrees. That's how you get a power factor of 1. But down here, the only way I get a power factor of 0, cosine 90 degrees. Or I can put a negative 90 there because remember cosine is an even function. So I can either have negative 90 or positive 90. Either one of those will give me a 0. Well, this can only happen when I have a resistor. And this can only happen when I have reactance. If I have an inductive reactance, it's going to be a positive 90. If I have capacitive reactance, it's going to be negative 90. But either way, it's 0. So the way to look at power factor is the power factor between 0 and 1. The closer you are to 1, the more resistive the circuit. The closer you are to 0, the more reactive the circuit. And it's important to know because when we get into AC power, what you're going to learn is this kind of power is bad. Reactive power is bad. Resistive power is good. So I'm not going to say any more than that until we get to power. But this I will remember, this little chart. I'll probably re-explain it when we get to power. But in the perfect world, we want our power factor, this right here, to be as close to 1 as we can. So, but the term power factor, we'll go ahead and we'll calculate it. So we'll calculate it. Power factor equals cosine of theta, T. So the theta was this phase angle in the voltage and the current, and it was minus 53.13 degrees. So let's do that. Cosine negative 53.13 degrees. Of course, if you want to, you can put a positive in there because, as I said, it's an even function. But somebody give me the value for this. If you put that in your calculator, what do you get? Cosine of minus 53 is what?
The 0.600.
Okay, so 0.6. Now, if you read the power factor, what he says is, when you report power factor, you got to use the term leading or lagging. Now, how do you know if the power factor is leading or lagging? You look at the current phasor. So let me go back. Let me put the phasor diagram back on the board. There's two ways to do this, all right? So you can look at the phasor diagram. Look at my phasor diagram. The voltage phasor is 100 angle 0. So let's put that back in there. It's right here. That's V hat. Your current phasor is 20 minus 53 degrees. So it's right here. That's I hat. And this angle is this angle right here, so minus 53 degrees. So remember what I said? Here you are. Here's your eyeball. I don't know why I can't draw eyeball anymore. When I was stabilizing, I could draw these eyeballs, but now my eyeballs don't look right. I guess because I'm drawing at this angle. Let me see if I can get a better one. All right, so there's your eyeball. And if this is my voltage phasor, and this is my current phasor, it's rotating counterclockwise, but that angle, that 53 degrees, is constant between them. So what happens is you see the voltage phasor go by, and behind that you see the current phasor, so the current is lagging. So when you report this power factor, you can't just write 0.6, you gotta say 0.6 lagging. Or sometimes you just say lag. If you don't include that, it's wrong. You gotta say leading or lagging. The other way to find this out is to just look at your net reactance.
And that's based
Here-
off of whether current is leading or lagging.
Say it again.
You said like
Based off the
yeah, I'm sorry, go ahead.
current.
Okay.
It's based off the current. If I draw my phasors, angle 0, there it is. My current that we calculated is 20 angle minus 53, so there it is. But this is a snapshot of it. Remember, these are really turning. When I draw a graph, it's like taking a picture of it, and I'm looking at the picture. The actual thing is turning. So we snapped the picture when it was like that. But this is turning counterclockwise. So here's my voltage phasor. Here's my current phasor. Here's your eyeball. If this is rotating, which one would you see first? The voltage. Which one do you see last? The current. So the voltage is leading the current, or you can say the current is lagging the voltage. That's one way to do it, is to use the phasor diagram. If you're a picture, what they call it, if you see pictures better than the phasor diagram, you can see which one's leading or lagging. It's always through the larger angle. It's always looking through, not through this angle, but through the larger angle. When that large angle gets around, which one do you see first? And if you look at the phasor, no matter where you are over here, you're always going to see voltage first and then the current. If you're confused by that, then it gets even easier. All you got to do is Eli the Iceman. So what you do is this. And this is for series circuits. Remember Eli the Iceman. This is for inductive reactance. and this is for capacitive reactance. What this says is if you have a net inductance reactive, my current is going to lag. My voltage is going to lead. If I have net capacitive reactance, my current is going to lead and my voltage is going to lag. So I see here I only have inductance here, so it's got to be this one. I got to use this side of Eli the Iceman because I only have inductance. Now, if I had capacitance in there, suppose I change the problem, I put a capacitor here. Put a capacitor of, I just dropped all my papers. Let's put a capacitor here of, I don't know, let's say 3 ohms. Now, what's my net reactance? Well, to find my net reactance, what I got to do is add up my net reactance. I got to add XL plus XC. Well, XL was 4, plus a positive J4. XC is 3, plus a minus J3. So I'm going to get a J1. And since that's positive, I still use this because that has a positive reactance. If I made this bigger, say I made this a 10 ohms, then I would have J4 for this, and this would be a J10. So my net reactance now is a minus number, minus J, which means it's capacitive. And I'd have to use this one and say that the current's leading. So because I only had inductance there, I can look at Eli the Iceman and say that my power factor was 0.6 lagging. And again, because of that little diagram I showed you before, the closer this is to 1, the better. Ideally, we want this to be 1. But you'll learn more about, why it's not 1. And there's ways that we can't really get it to 1, we can get it up higher. And I'll show you all of that. That's some just trig and stuff, but it can be kind of involved. That's later. Whew. Man, I feel like I've been talking. It's only 3:30, but 3:21. But that's all right. So that's a lot, guys. We did a practice problem, and we did some new stuff. Power. We talked about power factor, all of that stuff. So what I wanted to do, I think what I'm going to do, dropping everything. Let's see here. So we got I think I might have dropped some paper somewhere, but we do have a parallel circuit that I don't know what I did with it. It probably failed. Oh, here it is. I don't know if we probably could get this in. I think we probably should go ahead and do it, get it out the way. That way we can start. Well, I don't know. Then I got to explain admittance and all of that stuff. I'm kind of this. I think I got it set to 4:20. I think we'll be okay to do this. I think I had the session set to expire at 4:20, if I'm not mistaken, and not 4 p.m. So I think we should probably go ahead and do this. This is a lot of new stuff, and I don't want to give you too much in one chunk. But let's go ahead and, if we knock this out, then next time we can do series parallel together. So let me explain a couple things about AC parallel circuits, and then I'm going to give you some time to work on it. See if you can just use logic and what you know from DC to solve it, and then we'll solve it together. So let me talk about a few terms. All right, I'm missing a handout, so give me a second to see if I can see where it went to. All right, I'm not seeing it, but that's all right. All right, you guys remember when we talked about resistance in DC? There was resistance, and there's conductance. Resistance, we use the letter R. Conductance, we use the letter G. So resistance, if you remember, is the opposition to current flow. So resistance, what you're saying, how hard is it for the power source to push current through a certain material? Conductance is asking the question the other way. How easy is it to push current through a certain material? And the relationship between the two, R is equal to 1 over G, and G is equal to 1 over R. So when we looked at Ohm's law, you might not remember, we took 3 resistors, you made a graph with 3 data points on it, and we looked at conductance because the slope of the curve you got was conductance. It was, I think, experiment 5 or something like that. But when you deal with parallel circuits, we talk a lot about conductance, this G thing. So in AC, they do the same thing. The problem is, since we have more than one opposition, we got more than one term. So let me give you these new terms. All right, so just like before, 1 over R. Let me give you the letter. So we got R. We got conductance. We have susceptance. I have to read this because my spelling is terrible when it comes to my AC terms. And admittance. Okay. Conductance, susceptance, and admittance. Conductance uses the symbol R. Susceptance uses the symbol B. And admittance, they use the symbol Y. And you know this from DC, conductance doesn't use the R, it uses a G. I must be getting tired because I'm starting to make too many mistakes. So this is a G. Now you know from DC, this is 1 over R, right? But this is 1 over X. So this susceptance I get from reactive components. And this is 1 over Z, the impedance. So in DC it's just conductance, but in AC, I have conductance, susceptance, and admittance. And all these terms refer to how easy it is for current to flow back and forth to an element. Now, in DC, when we did this conductance, we said that conductance is 1 over resistance. And I know that the unit for that is the ohm. So it's 1 over ohms, and you can write that like ohm to the minus 1. That's the one I use for conductance. But they have something called a Siemens. 1 Siemens is 1 ohm to the minus 1. So a lot of books will use Siemens. I like the inverse ohm. I think it's cooler. So I'm going to use inverse ohms for the units. If you see in your book a S, they're using the Siemens unit. Okay? So Tell you what, guy. I think what I'm gonna do is just have you. I don't know if you have that sheet in front of you, but they give you a parallel circuit. And the whole idea of using these phasors to do my AC analysis is that phasors allow me to treat the circuit as if it were DC. So let's say you get a circuit and you have no idea how to solve it. Well, what you do is ask yourself this question. If this was a strictly DC circuit, what would I do? And the answer to that is, whatever the answer to that is, that's exactly what you would do in the AC circuit. The only difference is you got those angles you got to worry about. Remember, you got to deal with things in polar form and rectangular form. But the logic, the way you approach the circuit to solve it is the same as DC. So, said that, I have a parallel circuit. I have 3 branches in the circuit. One is a resistor, one is an inductor, and one is a capacitor in parallel. And they're going to have you find the total impedance. They're going to have you find the total admittance. They're going to have you find the total current. They're going to have you do all the DC stuff. So I think what I'm going to have you guys do is just go ahead and give this a shot on your own. You go ahead and try to do this, and then I guess what do we see? Wednesday we'll check it. I'm trying to think what was on quiz 1. Quiz. Yeah, I don't think you need any of this for the quizzes. I don't think I'm asking any of this stuff. I can't remember what I put up there. I think you'll be good to take this and just try to work this before next class. And I'm running out of gas a little bit. I'm used to taking a break every hour and all of that. So I'm going to let you guys do this. You know, I've introduced briefly the topics of inductance, admittance, and susceptance. I gave you the formulas for them. You don't need to know that, by the way. I'm just giving you the names in case you read about in your book. But what I am asking you to do is to, using your skills from DC and understanding that you can treat the AC as if it were a DC circuit, I want you to see if you can solve that parallel circuit for everything they're asking you for. Now, at the very bottom of the page, they do some more power calculations. They take you through the line of reasoning or logic that we apply to that problem we just did. So you should be able to, in theory, do this whole page, even the power section. You guys go ahead and do that, and then what we'll do is I'll just work this next class. I don't think I want to do it right now. So we're going to end that with that. Does anybody have any questions or comments or concerns before I turn the camera off?
I have a question.
Okay.
When we did the impedance diagram, when we drew it, we just used Z on the diagonal.
Yes.
Do we just leave it Z, or do we need to put the value?
You should put the value. I don't know what the value was, but you should put the value.
Yeah, because I think we marked the angle, but we didn't put the magnitude or whatever you call it.
Yeah, you know, if you give me a formal impedance diagram, you should put the value for. Now you don't have to do like say I gave you this. Say I gave you 3 components in series. Say I gave you a resistor, I gave you a capacitor, and I gave you an inductor. Let's say I gave you that. Say this was 100 ohms, this was 50 ohms, and this was 25 ohms. Okay, if you're going to find the total impedance, looking in this way, then your total impedance would be R plus XC plus XL, right? Well, when you do the impedance diagram, you don't have to show XC and XL. You can give me X net. So what I'm saying is, what you can do is you put the number in and say, all right, that's 100 plus, this is actually a minus, I do it like this, plus J, and this will be a minus 50. This will be a plus 25. Then I have 100 If I add these, I get a minus J25. So this is what you would show me on the impedance diagram. You don't have to show me that itself. So then what you would do is you draw your diagram and you say, my real part right here is 100, so I go over 100 units. That's R. Then this is 25 this way, so that's XC. But that's not really XC though, that's X net, because XC, if you look, is actually 50. So then when I draw my box, and then you do your diagonal, and then the diagonal gives you C. So you can show this right here as 100. That side of the triangle is 100 ohms. This side is 25 ohms, so you can show it as a minus J25. But yes, you should put this in the Pythagorean formula and show that side right there. And then this angle here, you would show that too. But you don't have to show these individually. Some people do, but you don't have to. Just show. What I want to end up with is that impedance triangle. That's what I want to see, sitting on top of that coordinate system. Okay? Anybody else? Well, I have another lab for you, but it's another video lab. I think I have, there's a video lab on the O-scope. I'm not really sure. we're gonna have to go up to the campus for at least one or two of the labs, because I don't know how you're gonna do AC without, you don't have an O-scope. And normally what I do is I pass out that lab that you did on complex numbers. And normally the second lab, I gave you guys a review on the digital multimeter, but normally it's my O-scope lab, which has you watch another video and learn some of the terms surrounding the O-scope. And then the third lab, we actually start to do the O-scope, but we won't be able to do that right now. So I have you do, I'm gonna have another video lab to learn about the O-scope. And then some of the AC labs, you can just use your digital multimeter, the ones with the capacitors and inductors. But at some point, you got to put your hands on the O-scope, and there's two O-scopes. There's an analog, which you learn on. There's a digital one where you learn the menus. It's menu driven. So there's no way we can do this by remote. So I've already talked to the lab tech, and he told me that to let him know when we want to come up there. Now, I didn't get it okay through the dean. We got to get an okay to get into the building, but I'm going to tell him there's no way we can finish up the lab without at least you got to do something with the O-scope. If not, when you get to electronics, you won't have any idea what you're doing. So that's going to have to, I don't know, I'll work it out and let you know. But what I'm saying to say is the next lab, which I'll put up sometime today or early in the morning, is going to be another video lab. And then the lab after that will be a hands-on lab. So if you still don't have your boxes, I know one or two people might not have a box yet. You're still okay. We still can get the next 2 weeks. I think will be all right. All right. Anybody have any other questions? Okay. Well, try to work that parallel problem. Don't just put it away until next time we get together. Try to work it, and that way when we work it together, if you got it right, it's just positive reinforcement. But if you get it wrong, you can see where you went wrong if you already tried to go through it. And then I don't know. I might start the class a little earlier. I might start at 1:30 instead of 2, and that way we'll have time we'll go into a parallel calculation, and then we do a series parallel, and then I think we might start power or something. I don't know. I gotta look at my notes. So you guys have a great rest of the day. Make sure you look at Blackboard, look at what I put up there, and then I will see if you have any questions or concerns. All you gotta do is send me a text. See you later. Thank you.